There. All right, so I'm really honored and humbled to be part of this master class. I do not really consider myself an expert on homotopy theory. But the thing is, there's some conjectures out there. They're generally due to Michael Hopkins. And they've inspired a lot of periodic geometry. And that really drew me into the field like a magnet. So I want to tell you about a version of some of these conjectures called the transchromatic splitting conjecture. And I'd like to discuss what p-adic geometry can do in the service of those conjectures. I'm going to start a little slowly with an introduction to some of the objects that get involved, namely Morava K theory and Morava E theory. And I encourage all kinds of interruptions and questions. Okay?
Interruptions suck.
So I'll start with a discussion of, as an outsider, how I understand the importance of Morava P theory. And here is the characteristics in the worlds. So I think of a certain analogy here in the category of abelian groups. I'm just going to call that AD. A characteristic is an equivalence class of division algebra objects D, and if I have a division, so I can talk about a division algebra object in this category. We should just call that a division algebra, as we classically understand the word. And equivalence might mean D1 is equivalent to D2 if the tensor product between the two is non-zero, yeah? So what are the characteristics in AB? It's pretty easy to see what they are. Some kind of generic characteristic 0, and this is represented by Q, or really any division algebra characteristic 0. And then you also get the special ones, P. And these are represented, if you like, by the finite field FP. And that's all there are. And with these characteristics, you can accomplish this notion of localization. So localization, as I've come to understand it in this world of spectra, sort of is a meld of the concepts of localization of prime and also completion at the same time. So the notion I'm referring to here is boost field localization. And if we have an object, there is. Something like correct me if I'm pronouncing it.
Ballast
field. Okay. Thank you. Ballast field. So let's have an object in the derived category of abelian groups. And some arbitrary objects. E acyclic. Simply if the tensor product between M and E is 0, such an object is E acyclic then. So this tensor product is derived, yes. And another object called X, is E local if there are no non-trivial homomorphisms from any acyclic object. So where I'm going with this is that we have some notion, probably familiar to everyone in this room, better than me, but we have this notion of localization at an object E. And the notion of localization is a functor from D of ab to a subcategory. So I could talk about this. I could write the ab sub E is the E local objects. And this includes inside of 2L. All right. But then there's going to be a left adjoint to this included, which I'll call LT. Yeah. So this is the Gauss field localization at the object. So let's just review how this works in the situation of these two characteristics here, so the role of E may be played by Eustace. Let's return to this board. Yeah. So the situation of Q is pretty easy. What would it mean for an object to be Q local? It just means that it's a Q vector space. And then the localization functor LQ. What does this do to an object X? Well, it simply tensors it to Q, so that it then becomes a Q vector space. And this kind of localization is smashing. It sort of acts like tensoring with some fixed object. But then there's another notion for the characteristic P. What would it mean for an object to be FP local? Well, it means that it's derived P complete. So if it were just a billion groups, just in one degree, that would mean that it's separated and complete for the p-adic topology. And then what's the localization function of LFP of X? Well, it's the completion of X at P. So this localization functor kind of does this kind of algebraic localization, but it also does this sort of completionalist. So if that's okay, yeah, then I'd like to move from this over to the category of spectra, and then just review what the characteristics are in that situation. So let's consider now SP, the category of spectra. The characteristics are well, we've got this kind of generic characteristic. So that's represented by Eilenberg-MacLane spectrum with Q. So that's like characteristics here. And then for each prime P, you have a bunch of other characteristics. One for each natural number. And these are going to be the Morava K theory. And for now, I'm notating them as K and P n. So it depends on both P and n. And the final one is that for each prime P, I mean, you can set n is equal to infinity here if you like, and you get the plane spectrum HFP. So this is the complete list of chromatic characteristics and representatives for each. So we kind of have analogies for this one and this one from the board over there, but then for each prime P, you get all of these infinitely many intermediates. And I could also refer to this as K of P infinity. And then in a context where the prime P is understood, I could refer to this as K of 0. Yeah. So relative to a prime P, you get characteristics indexed by numbers 0, 1, 2, ending at infinity. Great. So what I'd like to do is just abbreviate K of n. It's going to just be K of the end. And K of infinity is going to be this one, and this one will be K of 0. Prime P being understood in all these situations. So brings us to Hopkins's splitting conjecture. Well, there's a few things that go under this name, so maybe I'll write conjectures. One is like a simple fact that a certain morphism between spectra is split, and another says completely what one of the spectra is. But this is going to refer to what happens when you take two indices in n, and then I'm also going to introduce another index t. And the n here I want to be less than infinity. So I've got a pair of numbers t and n. The t is allowed to be t. And I believe I need to make some assumption here about the prime t, and maybe just for safety purposes, I'm going to say t is large relative to the number. And there's an isomorphism of ring spectra And I've seen this written in a number of different ways. So I'm first going to consider a, a derivative of the original conjecture, which is a little easier to write down. And I'm going to call this transchromatic. I don't know if that's the right term according to your ears, but for me, transchromatic means there's just two heights involved rather than a whole range of them. So this is going to refer to what happens when you localize the sphere spectrum at the larger K of n, and then localize it once again at the smaller one. This one. And this is going to be K of t local, of course. And the idea is that it should be isomorphic to something derived from simply the K of t local sphere. This means P complete the thing, more on that in a second. You're going to see a lot of copies of this. But a brief way of writing what I'm talking about is to say, I want this spectrum tensored with an exterior algebra on some number of generators. So there's going to be n minus t of these generators. This is supposed to be a graded ring. The grade of the degree of xi is going to be 1 minus 2 times xi. Now, I think that this notation deserves a little bit of explanation because what I've done is I've taken a spectrum and tensored it with a ring. So what does that mean? But oh, right. I didn't explain what the lambda meant. Lambda is an exterior algebra of Z. I guess that notation is standard in this room, but not in my world. But that tensor product means, okay, well, that exterior algebra is the free Z algebra. It's got a basis. So, okay, add up, take a direct sum of as many copies of this as there are basis elements. But apply suspensions. So, for instance, the copy that's indexed by just x1 shifted over by -1. That is d suspended. Take the direct sum of all of those, and then put a ring structure on that in the evident manner, using the ring structures on either side. So I don't want to write down every detail of that, but is that sort of clear? I can take a spectrum and tensor it with a graded ring like this to get a new spectrum. This is a ring spectrum, and so is that, and so is that. So this is what I'm calling just the transchromatic. Transchromatic splitting conjecture. All right, so this requires a little bit of context. It seems I've periodically completed this S, but I need to do that just in the case when t is equal to 0. If t is greater than 0, then this is already P complete and there's no need to do it. But if t is equal to 0, LK0 is just tensoring with Q. So on the left side, we get something P complete, on the right side, we would. So only in the case of t equals 0 is when we
Are we thinking S or LKTS?
We're doing it at this stage. Yes. It would be bad to do it. If t were 0, it would be bad to do it in the other direction. You'd get 0. All right. Are there any other questions about just this statement? So I have really grown to love this statement, and hopefully over the course of this lecture series, I want to explain to you why this ring appears with this number of variables. Hoping that p-adic geometry will rise to the occasion of really explaining what's going on. Now, let's continue over here with these. So the conjecture now known as Hopkins's strong splitting conjecture is a little different than this, and it's stronger than this. So the usually known
Your question about
great question. The question was, is there an evident match between the two sides? My answer to you currently is no, unless t is equal to 0 or t is equal to n minus 1. And those are the two cases I want to discuss in more detail. It's a little unclear to me where otherwise, you could try to write down a map, but to me, it's not canonical. So that's the difference for me. I mean, those two cases that I just they function way better. Yeah. Because it, of course, would be stronger to say, here's a canonical map from one side to the other, and we're claiming that it's an isolated. So in those two cases, we can do that. Yes.
Like historically speaking, it would be right to say if it equals 0, if there wasn't math, and a challenge to show that it's an equivalence.
Yes, I'm going to show you in this lecture what the map is in both of those cases. So I want to briefly say why this derives from your kind of original Hopkins element there. Strong, so this means strong.
Look at the area algebra. What is the definition of the area algebra where the ratios are in different degrees?
Oh, okay, so algebraically, it's just the exterior algebra. The rating on it is determined by this formula. So,
So what is algebra because these guys live in different homological degrees. Then so what is the definition?
It's a tensor product of a bunch of exterior algebras. This is a short form of it.
oh yeah, that's right. You could actually write, well, the question is, what does this mean? I mean, you can imagine what lambda of just x1 means. It has a degree 0 part and a degree -1 part. Now take all of those and tensor them together, that's all.
So what ring structure does it estimate?
Oh, it's simple. The product of any xi with itself is 0, and that's the only relation. So it's a commutative graded ring.
Okay.
The free commutative graded ring on these generators.
Those generators agree with each other, right?
The generators anti-commute.
And you can.
Well, yes, they make a commutative graded ring.
That's
Yeah. Yeah, they're all an odd degree, so they anti-commute with each other.
So it can be good at the square there is potential. Right?
Yes, so each of these lambda of x sides is a square 0 extension. You see, that's cool. Others? So the strong splitting conjecture, so it's something like this. It has to do with when you take this smashing localization. So let me explain what this meant. I have Ln. This is localization at a bunch of characteristics all at once. So everything from n0 to n. And the strong splitting conjecture concerns the n-1 localization of LKN of the sphere spectrum. This should split, as a direct sum. So really to do the thing justice, I do need a little bit more notation. So it's the sum over all subsets of integers from 0 to n. And for each one, I'm going to give the tensor product over all indices in that subset. And then I'm going to suspend 1 minus 2i. And then I'm going to take the n minus ith localization of the p completion of this field here. So this is how basically how it appears in the literature, especially the article by Hovey and why does this apply to this? Okay, so omitting some details. To get the transchromatic version, just going to apply LKT to both sides of this conjunction. And we have to note something if when I take the KFT localization of something like this, it's like the KFT localization of the S localization of something. Well, that's just going to be it's just going to be the same as LKT. Well, T is less than or equal to S. It's going to be 0 otherwise. I mean, the idea being that S is smaller than T, then localizing again at KFT when T is larger than S, it's just going to kill them. Otherwise, it's this KFT local. Some of the terms die when we apply LKFT to both sides, but what remains, if you're careful about the indices, will look like. Okay, So this is fantastic. I'm very curious to know to what extent you can prove this using this, but I honestly have no idea, and that seems kind of hard. So I'm just going to focus for these lectures on this statement. Let's leave this one go. Okay, what do we know so far? Oh, and yeah. It would be great to know this conjecture. What's the motivation for it? Well, we're interested in, for instance, the homotopy groups of spheres. We can p-localize and try to get the homotopy groups of a local sphere. And there are approximations to this given by the Ln of the spheres. And there's I've written all this down, but I think I think it's standard material in this room. You can ask me about it in discussion tomorrow if you like, but I have a motive that there's like a pretty good motivation for why I would want to know this. That was very interesting to me as I was learning. All right. So some known cases of this. So this conjecture above, the strong chromatic splitting conjecture, the thing right above, this is a theorem. For n equals 2, with an appropriate modification. Going the prime p is 2. I mean, it's not going to be correct as stated. And this is theorem of Beaudry, Nurse, and quantity. That's not considered this. For larger n, I can tell you something about this conjecture. The transchromatic splitting conjecture is a theorem for all n. And this is my recent work of L. Stapleton and myself. So that was the project that got me started into this whole business. So when t equals 0, what we're doing here is just tensoring everything with Q. And so we want to know what are the rational homotopy groups of the K local sphere, and that was the problem that was solved. Not connect to that one. So we're going to discuss that work also. And then so here, even the p equals 2 case here. Here, p is anything.
Right.
After all, we've inverted. We've rationalized everything. I'm funny this. Oh yeah. Right. I should make the same description about p versus n. Right. And in truth, I don't know the correct statement that would be true for all p. I'm not sure that, and I'm actually not sure that there should be a good one. And then for t equals n minus 1, I want to report on some work in progress. So last December, I co-organized a workshop at the American Institute of Mathematics in California, and some people were here. And there was a really large collaborative project, and over the next few lectures, I want to talk about some of that work. Not yet, theorem, but very promising. All right, questions so far? Much time that you've done. Oh my gosh. Okay. So I think I better start talking about the meat of the matter, which is formal groups. So we're going to discuss formal groups, and then I want to talk about the algebraic statement that you can reduce this statement to. There we go. We'll have to do this.
They're coming, they're coming.
All right. So the entry point into number theory is through formal groups. I wrote a review of what formal groups are. Does everyone know what formal group is? No? So let me just highlight the main things that I need from this theory. So for one, I want to talk about a formal group of a particular height over an algebraically closed field of characteristic P. So we're going to start the discussion over a field like this one. Well, maybe I'll just put it this way. Yeah, over FP bar, sure. It's well known how to classify formal groups. There's exactly one formal group, and I'll call it gamma n, and it lives over K. Of height n, 1, 2, 3, and so forth. So this uniqueness is up to isomorphism. So we want to not just say what the isomorphism classes are, but what the entire stack of formal groups of height n is. So for this, I mean, it's a pretty well-known story, but I do want to review it. Formal groups over a perfect field correspond to certain Dieudonné modules. So I can model what gamma n is through its Dieudonné module. But let me write M for the Dieudonné module of a formal group over a field of characteristic P. So this is supposed to be a module over the Dieudonné ring. So that Dieudonné ring is like the Witt vectors of K, yeah? But then I have to join an F and a V modulo, of course, the condition FV is equal to P, right? But so I want this to be a cyclic module over this thing. So there's one other relation, and how about F to the n is equal to P? That's a good one. So that's a quick way of modeling what our formal group is. I can just write down what its Dieudonné module is. I hope everyone can see this. I've just imposed the condition that the Frobenius map, when you raise it to the nth power, you just get a P. That's good a model of that. So I also want to know what the endomorphism algebra of this gamma n is, and that's easy to write down as well. So you just have to figure what all the endomorphisms of this as a Dieudonné module are. Such a thing would have to commute with the action of F. So of course F itself is good, but then it also, what coefficients can be used? It could be, you could use the Witt ring of Fp to the nth, because that's going to be compatible with this condition. So I can write what this endomorphism algebra is. So the Witt ring of Fp to the nth. But you have to adjoin this element F, and then mod out by this relation F to the nth. And then I should explain something, which is that this F is not going to commute with the elements there. It's going to act as Frobenius. But this is a non-commutative algebra. So again, I hope this notation is clear. Please let me know if it's not.
So in the duodenum module, F also acts frobenius-limiting.
Yeah, that's right. So I mean, maybe
Okay.
sometimes you see a different notation for this, maybe using angled brackets. But the F is supposed to act as Frobenius on its K. And the V would be the inverse to that, right? So it's the same story over here. So it's pretty easy to write down generators and relations for this endomorphism. I want to write this as a ring of integers in an algebra D. The D here is just the OD invert P, and this is a division algebra over the p-adic rationals of invariant 1 over n. And that's a neat way of telling you exactly what this n is. There's one isomorphism class of division algebra for each of these invariants that I could write down. So how about 1 over n?
So can you define what is the invariant of a division algebra is?
Sure. So yeah, so this is actually referring to something in local class field theory. These central simple algebras over QP, or really over any field, are classified by the Brouwer group of that field. And we're just saying what the Brouwer, I'm just going to tell you what the Brouwer group of QP is. It happens to be isomorphic to Q C. And this map is the invariant map. So I'm taking out the element 1 over n from here. So over here, it's an element of the Brouwer group, and you can represent that by a unique division algebra. And this D is that division algebra. Its rank n squared, and its center is Q. Okay. So all of this is very well, pretty well known. And we have perfectly good generators and relations for this group. So, of course, the automorphism group of gamma n is a group of units in here, and that's a p-adic V group. That's pretty interesting. And finally, I'm going to introduce the Morava stabilizer group. So that's a thing notated as gamma n. Oh wait, yeah. So this is the automorphism group, not just of gamma n, but of pair K together with gamma. So if you like, it consists of a pair of elements. One is an automorphism of the field K. The other is an isomorphism between the formal group gamma n and its pullback via the automorphism. So it fits into an exact sequence that looks like this. It maps towards the automorphism group of K, which is just Z hat, it's the Galois group of FP. And the kernel of it is going to be this OD cross. This one of the exact sequence like this. This is a procyclic group, so it's even splits, so it's a split instance. And sometimes I want a special name for this OD cross without writing this section. I think SN is sometimes used, but I want to write SG. I think S might get confused for the sphere spectrum. So, maybe you don't like this so much. It's sometimes called SN, yeah?
I like that better.
You like this better, huh? See?
Most of it, what would you denote the kernel of the determinant homomorphism on?
I would put an upper 1. I would put an upper 1 for that. Yeah. Okay. Like so. And that's going to come up later. All right, great. So, one reason this.
Why do you want to give it a special name?
I don't know. It'll come up in a second. This GN. Yeah, so I can present its significance as follows. If I consider the moduli stack of formal groups of dimension 1, that's this MFG, right? So inside of it, I can consider the moduli stack of formal groups which are in characteristic P and their height is exactly n. So this is the stack which classifies formal groups modulo P of height exactly equal to n. So what is that? So I mean, I just said there's only one over an algebraic group. So a way of summarizing everything on this board is to say that this is the quotient stack of spec FP bar by the Morata stabilizer group Gn. So Gn knows how to act on FP bar, that's what this K is, it's FP bar. And this quotient stack exactly classifies formal groups modulo P of Huygens. Okay. So that's formal groups. Everything will be What about definitions? Where is this all leading? I'm going to tell you about neural E theory. You know better than I. Definitions. So the study of deformations of a formal group traces back to the work of Lubin and Tate in the 1960s. So I'll just state their theorem again. Deformations of this formal group gamma n are parametrized by asserting the Therian local ring. I'm going to call that local ring AN. And Lubin and Tate determine the structure of that local ring. It's an algebra over the ring of bit vectors, and there are n-1 variables there. The variables themselves are not really well defined, but you can make it so that their order is well defined. And then the ideal generated by the first t of the variables is going to be well. And this notion of well-defined might just be that it's Gn invariant. So you see, since Gn acts on gamma n, it acts on the whole deformation problem. So I might write that the Gn here acts continuously on this thing. Oh. And then to write a line that mimics what's going on over here, I want to say the following thing. If I write mgn, but I put a hat over the n, this is supposed to mean the completion of the moduli stack of formal groups along this locus NFGN inside of its fiber modulo K file. So that locus, it's locally closed inside of here. It's like a completed plot. It's sort of a funny business, completing along this only locally closed thing. But you can do it, and the end result is just going to be this n hat. What is this n hat? It's isomorphic to, well, it'll be a formal spectrum of AN, and then modulo P. So I kind of first saw this fact referred to in a short paper of Laurent R, and I was like, oh yeah, that really clicks in for me. I never really saw a formal proof, so I wrote one up in the second paper I had with these same collaborators on the Picard proof, the KM local cat. It's actually somewhat of a non-trivial.
When you write stuff, what is back to which one you want?
Great, okay, great question. So there's some missing information on this. So AN, I want to give it the IN topology. So the maximal ideal, that'll be the thing generated by all the variables, including the P. And so I want this to generate the topology. So that's the topology.
Which is it?
Oh, yes. So you could even do coarser than that. You could do the pro-étal topology. This Gn is the profinite group. So all of these objects have homotopy theoretic avatars. So the familiar one in this context is Murad Easy. So here. So so this En is a commutative ring spectrum. What's its homotopy ring? Well, I want to write it this way. Oh, now I realize that I need one more piece of notation. So I'm going to make an adjunct to the board above. And I want to give a name to the universal deformation. So let's call that gamma n tilde. What's over there? So this En lower star, it's going to be some graded ring. What is it? So I mean, canonically, here's what it is. It's built out of An and then a bunch of three An modules of rank 1, namely the tensor powers of the Lie algebra. So you get the direct sum over all indices I of the Lie algebra of gamma n tilde tensor I. So this Lie algebra is free of rank 1 over An, so maybe it's silly to just write it this way, but I don't know, this is canonical, otherwise you have to make a choice. But if you do make that choice, maybe you choose a generator for it, so let's call that beta. And then more familiarly, you could just rewrite this as N, and then it's Laurent algebra over one thing. The degree I want for this beta is -2. This is the familiar way.
And is that sort of just for fun, confusing like a formal parameter further?
Yeah, so it's kind of the difference between a formal group and a formal group law. In the formal group law, you've chosen a parameter, and that's kind of like choosing this beta. Once you've chosen it, then you do get this kind of thing. But you know, the Gn action, so Gn acts on everything in sight here, and it kind of acts on B gamma n a little bit non-trivial. So just knowing the action on An, it's not automatically tell you what the action on An beta. All right, there is going to be more data on what the relationship between this En and the gamma n is. But why don't I just try to fit it all in here and just say that En is a complex oriented theory. And for such a theory, you have a good notion of Chern classes. So you can consider the universal line bundle over the classifying stack of line bundles, that's CP infinity. And the Chern class of that universal bundle gives you a class of En, the second cohomology of CP infinity. And that's going to generate the whole cohomology of CP infinity over En star over this thing. And then multiplication among line bundles gives you a formal group. I was going to write all that stuff, but I'll run out of time for you. That's what we have discussion on. I'll just write this one sentence. En is a complex oriented theory whose corresponding formal group is exactly this universal deformation of gamma n. All right. the relationship to the problems in the introduction of this talk has to do with the Devenitz-Hopkins spectral sequence. So we start with the fact that En is K of N local. So I'm gonna continue writing. So there's a unit map, and of course there's a unit map from S to any ring spectrum, so it's certainly such a map, but since En is K of N local, the map factors through the K of N localization. And the theorem of Devenitz-Hopkins four is that you can just obtain LKNS as the homotopy fixed points of En under the Gn action. And again, I see I've forgotten to write something. It's that the Morava stabilizer group acts on the sub. So this notation is homotopy fixed points, but the real subtlety for me learning this material is that Gn is not a discrete group. It's a profinite group. And this kind of homotopy fixed points has to take that into account. And I never learned, ever, the appropriate formalism that just does that. All I've heard is people just whispering condensed spectrum to me. How much literature is there on this subject? None. Could someone in this room maybe like write a thesis on that? That would be so great. Because currently we're all doing like weird ad hoc stuff to get around that. But I really want to say something like En is complete for the topology, the I-n-adic topology, and Gn acts continuously on it. Go ahead.
I think there's a particularly neat solution for describing this particular action
Yeah.
of Gn on En, the condensed way, which like at least two ways.
Sure, I don't no doubt it exists. It's just a question of did someone write about
I believe it appears in a paper, more.
Yeah, exactly.
it? Eat some of them more. I'll just look that up. These are my
We don't quite need them to write it down, because we can, there's the whole formalism of adic infinity rings and continuous actions on those.
Okay, so maybe you don't need to go whole hog with dense math. You can say
Yeah.
something about the spectrum is complete for there's the action of some ideal.
Yes.
All right, very good. So, I mean, I feel like the next math is going to get involved anyway, because the next step is to pass to something involving continuous column. So, the result of this is a spectral sequence that goes like so. And what I'm getting at with this topological stuff is that the homotopy groups of En, they have a topology on. And Gn acts continuously on all of them. So this continuous cohomology makes sense. You should get a spectral sequence list. What I was asking for with that comment is something that makes this complete formalism rather than having to do something like ad hoc to achieve this.
Or maybe I'll something naive, concerning the computer system. Your thing, I don't know whether I understand correctly. I mean, your thing is not necessarily connected.
Which thing?
No, when you talk about completeness, I mean,
Oh, completeness.
because UI, I'm not familiar with this, but your reading is like not negative if I were. That's correct. I mean, because the classical is the argument that the invention is something like workforce collectively. So I mean, not sure whether it works out.
I don't know either.
I mean, the approach Robert's never mentioning is more sophisticated than that.
There's no works for non-connective rings, and most of the time you can just reduce the connected capability of the periodic.
All right, so we can Oh, so this EN is periodic, it's not connective, but maybe you can reduce to that case. It still sounds kind of ad hoc. That's enough. Yeah. Really stand behind my desire to get it. So that this is a formalism. All right, so maybe this is a subsection, but. Reduction of the. Okay. Yeah, I like writing this as transchromatic split injection. With T equals 0. So in the T equals 0 case, we're interested in the K of 0 localization of the K of n localization of that. What is that? So K of 0 localization is just like tensoring with Q. So I can take this entire spectral sequence and tensor it. The nice thing about that is that you have a great handle on many of these cohomology groups. A lot of them go away. And in fact, the spectral sequence after tensoring with Q degenerates on the E2 page. So that's what I'll just write here. The above spectral sequence degenerates at the U2 page. And what's left is this isomorphism. Say exactly what the the rational cohomology of the K of n local sphere is in terms of continuous cohomology. So we get that the homotopy ring of the K of 0 localized, K of n localized sphere should be isomorphic to the continuous cohomology of Gn acting on any that tensor that's with Q. So so in this previous sentence, I said something about that spectral sequence collapsing, so you just get an isomorphism like so. And that shifts the focus to just questions of like what the continuous cohomology of the Murata stabilizer group on K is. And then the transchromatic splitting conjecture predicts what this is. It should be just Q tensor lambda, the exterior algebra on such and such many generators. And before. So why on earth would this ever be there? I mean, beyond just saying, okay, well, it was conjecture there, I can give you a quick justification for why such an exterior algebra should appear. So that AN here certainly contains within it the ring of Witt vectors of K. So remember, K here is FP bar. So there's at least a map from the continuous cohomology of Gn with coefficients in just this, the ring of Witt vectors. I mean, there's at least a map from one to the other. Yeah. And, the action of Gn on An is really difficult to get a handle on. Like, formulas are hard to come by when n is greater than 1. But here, the action of Gn on W of K, it's essentially trivial. So actually, I mean, the part I was calling SGN acts trivially here, and that SGN is a p-adic Lie group. The continuous cohomology of p-adic Lie groups was studied in the 1950s by Lazar. And you could use Lazar's results to show that after tensoring with Q, which I should have done, you just get the p-adic field, the p-adic field tensor x1 through xn. That's what appears over here. In brief, what's going on? We're taking the continuous cohomology of a p-adic Lie group with basically constant coefficients. Lazar cleverly knows how to compare that cohomology to Lie algebra cohomology. The Lie algebra cohomology in this case is a twist, an inner form of the group GLN. And the Lie algebra cohomology of GLN is well known, it's just this. So in a tight nutshell, that's what happened on this. So that's a hint as to why this kind of exterior algebra. But I'm not satisfied with that. I want an explanation that goes up and down through all the cases. So in the last 5 minutes, I want to talk about the other extreme when t is equal to n minus 1. So I can do this.
So does this give a more explicit description of the exterior part? As some sort of not just this exterior algebra, but as something more geometric?
Well, oh yeah, it sounds like you want to know what these x's are, in a sense. And that's a little hard to do. I think they're pretty inexplicit and they rest upon choices that had to be made. Yeah, quite a few. You kind of choose a uniform propy subgroup of this, and you choose various bases. So it's actually kind of hard to say exactly what these x's are.
But it's not like something that's a GLN somewhere in the background that you would actually.
There is the GLN. That's what this talk is about.
Okay,
So, in some sense, it's a great that you brought that up. In some sense, this is a hint, but it's actually kind of the wrong reason that this exterior algebra appears. The right reason is that you actually get the continuous cohomology of the group GLN-ZP. But to fully understand that, we have to generalize what's going on to the case of general T. Great. So the next subsection is reduction. In the case, t is equal to n minus 1. Same story, but now t is n minus. So in this case, I want to consider the following ideal inside of the Leben-Tate ring. So take all of the variables except for the last one. So I guess that's t through un minus 2. If I were to take the quotient of an by in minus 1, I would get k and power series this last variable. And I want to write this as the ring of integers in some local field capital. Capital K is going to be lowercase k Laurent series the same. And this is a local field, it's in characteristic P, it's got a topology, and a continuous action of the Marat singularity. So, we haven't proved the transchromatic conjecture in this case, but what we can do is reduce it to an algebraic statement. Okay, what is that statement? So, first of all, there exists a natural map, and then also that it's an isomorphism. That is, there exists a natural isomorphism. Okay, maybe for suspense reason, though, I'm right. All right, so the mysterious part is over here. It's the g acts in some mysterious way on this k, and we want to take the continuous cohomology. That's the thing that's going to capture the homotopy groups of the k of n localization of the k of n locals, k of n minus 1 localization of the k. That's what's going on. On the left side is, surprise, the group SGN minus 1. And then for fun, another combination. This. Just deal with this. Yeah, rid of that. All right. So the conjecture is that this is an isomorph. I better. Oh no, gosh, I beg for like 1 more minute.
You can have
What?
you can have a couple more minutes to start it.
Right. So where on earth did this come from? So Gn minus 1 is the Morava stabilizer group 1 height down. Right? All right. So at the very least, what I want to do is describe a map from one side to the other.
No, that Viking, you know.
What? I don't bite with my arm. Okay. So, right, so where's that? Range proof come from? So, I want, it involves exactly what happened when I formed this field. Okay? So, remember that gamma and tilde was the universal definition. So, of course, I can take that universal definition and extend it from AN to K, right? In other words, mod out by the ring IN minus 1, and then invert that last pair. Oh. So this new formal group has height n minus 1. That's the thing. So just this observation. And yeah, actually, everything that's happening here, there's an article of Tori, I don't know if I'm pronouncing that right, where a lot of this material appears, so it's not exactly that original. But this has height n minus 1, it's a formal group over a field of characteristic P. You can trivialize that. In other words, there's only one formal group of character of height n minus 1 over an algebraically closed field. So let L over K be the extension that parameterizes isomorphisms between this gamma n tilde and gamma n minus 1. It's height n minus 1, so there should be some torsion. L over K should be a Galois extension, where the Galois group is, all right, here's what it is, Gn minus 1. We've already, the base field is already FP bar, so that's why this, not Gn minus 1 up here, it's S Gn minus 1. This is the automorphism group. Yeah. So L over K is this infinite Galois extension with this Galois group. So I could write something like, hey, it's just the homotopy fixed points of Gn minus 1. SGn, I'll have to play with that. S Gn minus 1 in 1000. Basically because of the normal basis theorem, there's no higher finish on this word.
That's the last one.
It's the last one we can't finish up, but.
Handing out force over there.
So here, I want to conjure up the continuous homology of that product group. That's like so. And I'm gonna, so I mean, FP maps towards L, of course, because L is an FP vector. And now the SGN minus 1, I'm just going to carry it. On the other hand, ZP star receives a map from GN. Here's the norm map. Maybe you just have to believe me, but I think in applications you've seen that there is a norm map out of the Morales landing in ZP star. So because there's this norm map, and the ZP star here is supposed to be acting trivially on this FP, both of these groups are acting trivially here. So I can get a map from these homotopy fixed points towards these. Okay. On the other hand, by what I wrote on that board over there, these two, these two confused together, and this is just K, HG. So I've given you a map from here to here in terms of continuous cohomology. It's a map from there to there. All right. Well, over the next couple lectures, I'll say a lot more about these two cases, the t equals 0 and the t equals n minus. Thanks so much.